All right. Okay. Yeah. Last meeting. So, good luck as you guys are studying for the final. We'll see you guys on Thursday to take that, and I'll send out an announcement. But we'll just use the same seating chart from the midterm, and pass out the exams, and you'll take it, and we'll be done. Okay. Apparently, in the syllabus, I made a mistake. So this was brought to my attention. I didn't even realize, it's like you write things and you don't double check, and then you're like, oh, I'm a dummy. But apparently, if you look at the grade breakdown, it doesn't add up to 100%. It adds up to 90%. So that was my bad. So I'm gonna, you can just put in 10% free. So I'll just put in everybody like a baseline 10%, and then this 90% will just go on top of that. All right. I don't want to like readjust weights, and just in case somebody did like poorly on their midterm or something. I don't want to or I don't know, whatever. So I feel that's like because it was my bad, right? So we'll do that, and that should be fine. Okay. And then I think homework is the last homework is due on Thursday as well, so get that in, and then I don't know. Okay. All right, let's so today's lecture example, it's just kind of like a random thing. Doesn't actually isn't not necessary, but just kind of a fun little thing. And so there's this package called Imager that allows you to kind of load images into into R, and then you can kind of play around with them, and it'll basically import an image, and you can basically turn it into just like a giant matrix. Okay, because like every pixel being a cell in the matrix. So most images are like highly compressed or like have certain algorithms so it doesn't like take up a bunch of space, but when you bring it in with this and load it as a matrix, it just takes up like a whole bunch of space. Because if you imagine like a 1 megapixel image, which isn't very big, but that's basically like 1,000 pixels by 1,000 pixels is a million pixels. That's like a million values in your matrix. And then a lot of images actually have 3 color channels, a red, a green, and a blue. And so you'll have like 3 million values inside this thing, and they all go from 0 to 255 or something. But anyway, it allows you to kind of work with these things. And so I thought it would be kind of a fun, I don't know, just kind of like of a weird way to think of image compression through the eyes of principal components analysis. Okay, so again, with principal components analysis, what we're doing is we're taking our data. You imagine you have a matrix of data, and you have all of these columns, and they're correlated, and you decorrelate them. You like find like a lower dimensional projection that tries to retain as much information as possible, and takes advantage of like the correlated structure. So if you think about like an image as columns of pixels, basically most columns will have high correlation from, like, if you think about it, a picture and like a picture of my face or whatever, and you think of like this thin little vertical strip of pixels, and you think of like the column of pixels right next to it, most of those pixels will probably be very similar to the pixels to the left. The only time you'll have like a big difference is if there's like a vertical line or a boundary, right? It's like if your image is of a building, when the building ends and there's like sky next to it, that's when they're like, you won't have high correlation. But like if you think about like the sky, like all of these pixels will be highly correlated because it's probably mostly blue. Maybe there's a cloud, and so things change a little bit. So you're gonna have lots of high kind of correlation there. So anyway, I thought we'll just kind of see what like dimension reduction looks like, and in terms of like data compression for using principal components analysis on an image. Now, this is theoretically possible as a way to compress image data. It is not actually used in practice because of the high computational cost of figuring out eigenvectors, eigenvalues, and doing that kind of like compressing it and then taking the compressed thing and then reconstructing the full thing. It's like kind of computationally expensive, so anyway, it's not how we do image compression today, but it's just kind of like a fun idea to kind of play around with. So anyway, what I'm going to do is I'm going to load in this library imager. This script is posted on Brew and Learn or Canvas, and as well as the image. And so here is an image from Ansel Adams. I don't know if you're familiar with the photographer Ansel Adams. He has a lot of kind of pictures. He has like some really famous kind of, he did photographs in like black and white, and he has like some beautiful pictures of like Yosemite and some of these things. But anyway, one of them is Snake River, the Tetons and Snake River. So this is his picture from Grand Teton National Park. It says one of his best known and most critically acclaimed photographs. So anyway, this is the image, and we're gonna do we'll load that in. So I call in load image, and so inside R I now have this. Let me clear out. I now have this image object, and it's like this big array, 899 by 720. So it's 899 rows, 899 columns, 720 rows, and there's there's a 1 here. It's because there's one frame. It supports like you can imagine like an animation where you have like one image and then another image and another image, and then there's 3 color channels, up to 3 color channels. But here, because it's a black and white image, it's going to be grayscale, and red, green, and blue all have the same values. So anyway, I'm going to just take the 899 by 720, okay? And so I'm going to just make that as an array, and then we'll put that in. Oops, I have the pixels incorrect there. And so it just says large matrix 647,000. So if I do 899 times 720, that's 647,000 pixels, okay, or values in a matrix. But we can take that matrix and we can make an image out of it. Oops, I gotta try this again. And so this gets plotted in R, using baseplot. And so you have like the pixels on the left and right. So this is 899 pixels this way, and 720 pixels vertically. And so this is what the image looks like. And so what we're going to do is we will run through this. We'll do principal components analysis. So what I'm first going to do is I'm going to center the matrix, which means I'm going to just treat this as a big matrix with 899 columns, and I'm going to subtract off the column mean from each one, so that each column will have a mean of 0. Okay, and I can just kind of center that, so I have Atom centered, and I can just double check and make sure that it is centered, everything's equal to 0, and that comes back true. If I want to, like, I could plot the centered image as well, and it's a little hard to tell what's going on, but it looks like the same image, and I don't know if you can tell in this with this projection. It's a little bit hard to tell, but there's kind of these vertical streaks of like lines that are a little bit darker or a little bit lighter. And so, for example, this area is a little bit darker than the neighboring areas, and that's because, you know, in the original image, okay, so if this is the original image, like, you think of the column average of, like, what's the average value of all the pixels in this column, and because there's like a lot of dark pixels, it's like if we imagine, I don't know what the values are, but let's say black pixels have a value of like 0, and then bright pixels have a value of 1 or something like that, right? So like the average of this column where there's a whole bunch of dark pixels is pretty low, whereas these columns, which are you know, have more kind of bright values, have like a higher average. And so when we kind of subtract off the column mean, we end up getting, I don't know if you can see the difference between, this is the original, and then or subtracting off column means, and then you get like these slight vertical streaks. Okay, so anyway, this part ends up being a little bit brighter. This part where there's kind of some brightness down here ends up a little bit darker, okay, versus the original there. Okay, so anyway, that's what happens when you center the image and you're just subtracting off the mean of all of the columns there. Okay, and then now that I have this matrix, I'm going to ask for the covariance matrix. Okay, invalid graphic state, I don't know what that means. I don't think that has anything to do with the covariance. So I could, like, this covariance matrix it's a even bigger, 899 by 899. So there's even more values in the covariance matrix, 808,000 values in it. But I'm going to ask for the eigenvalues and eigenvectors. Okay. So it takes a moment, and then and so if I ask for the eigenvalues and eigenvectors, I have 899 eigenvalues, and I have 899 eigenvectors, each of length 899. Okay, and so if I wanted to, I can keep just, let's say, the first 50 eigenvectors. Okay, so I'm going to take all of these eigenvectors, and this is a big matrix, so with 899 rows, 899 columns, I'm going to just keep the first 50 of them. And so, so now the amount of kind of data I have is going to be 899 by 50. So what is that? 899 times 50, basically about 45,000 values, versus in the original kind of matrix has 647,000 values. So, you know, 1/10 of the values. And so I can take that and I can project the image down onto those 50 how do I keep saying this? Okay. Down onto those 50 principal components, okay? And so now my, once I project it down, now I have 720 rows, okay, of 50 values. Now, if I try to, if I try to plot this, it would make no sense whatsoever, because this is some weird lower dimensional shadow of the original data. Okay, so this I projected. Okay, so this I'm going to plot the data projected down to 50. Okay, and it is like nonsense. Okay, because basically I've got 50 columns of uncorrelated data. Okay, and so this isn't, it's not like some optical illusion where, like, if you look at it from the right angle, it's going to suddenly look like the original image. No, this is like just total nonsense. Okay, this is like, I guess if you were a being that lived in 899 dimensions and you could see these lower dimensions, then you could see it, okay, in the way that, like, we can see a two-dimensional shadow and make sense of it, right? I don't know, have you guys heard of like flatland as like this analogy of, like, if you're a two-dimensional being, like, you only see like stuff this way, right? But here it's like, yeah, we live in only 3 dimensions and we're seeing images in 2 dimensions here, and it doesn't make sense. But anyway, so this doesn't make sense. But what I can do is I can take this lower dimensional projection, and it's kind of just like, you see a shadow cast on the ground, okay? And you're like, okay, based on, makes any sense at all, but like, okay, based on this shadow that you see, let's make a 3-dimensional thing. And basically, like, you would just take this shadow of my hand here, and you would like cut out a piece of cardboard or like a wooden plank, and you would have it's still going to be a flat thing, but it will kind of resemble like an actual hand, right? It's not going to be like, the fingers aren't going to be round, they'll be just like basically a piece of cardboard that's thick, okay? But I mean, you might have a certain thickness, but now you have this kind of paddle, right? Hand-shaped paddle that resembles like a hand, okay? Whereas if my shadow doesn't look like, if I did the wrong shadow and I did this and I cut something like this out of the cardboard, then the cardboard paddle doesn't really look like a hand, right? So yeah, like, I don't know, you have like the foam finger and it's a flat thing, but it's like, oh yeah, that's a foam finger that's pointing, right? And it's kind of like that. And so anyway, basically we're gonna take this flattened version and then turn it back into the higher dimensional version, okay? So the way we do that is we take the flattened version, this projected version, which is basically the shadow. We're going to multiply it by like this undo transform, like the transpose of it, and we're going to kind of get our recreated image. And so this recreated image is now back to 720 pixels by 899. I subtracted off the mean, so we'll add the mean back in, and then we will plot that, okay? And so this is the image after we reconstruct it, which resembles the original image. If you look closely, it's kind of fuzzy, it's kind of blurry, and that's because, well, we reduced it down to 50 dimensions, and then based on that, we're trying to recreate the whole thing. And so you lose a lot of that fine detail, right? Again, like if I cut out my hand and I cut a piece of cardboard out of it, it, or a piece of wood, a wood plank out of it, it'll have the shape, but we're gonna lose some detail. And that's basically what's going on here. So let me delete this one, and let me delete that one. Okay. So here's the original image, and here's the, I don't know if you guys can see it. It looks better on my screen, but so here is after we've reduced it down to 50 principal components and reprojected it, and this is like the original. Okay, so there is a slight difference. So so I wrote a loop that says, all right, let's try this out again. But what if I just kept one principal component? What if I kept two principal components? And again, it's like, okay, if I just project this down to one principal component, so basically I just have like high or low, and then I project it back to 899 columns, like what kind of structure will I retain? And so, so I did this. So here I can run this loop again. And basically so for each of these things, I just keep one of the vectors, I project it down, and then I save it. Okay. Yeah, actually, I don't want to do this. So so I ran this earlier, and this is, if you keep one principal component, so here's the original image. So if you keep one principal component, this is the resulting the image. Okay, so you lose a lot of information, but it retains, like, okay, this area is dark down here, this area is bright, and this is kind of gray. Okay, all right, with two principal components, we get more. So we have like, oh, here are some bright areas, okay, dark areas, and then brighter. Okay, so, and then here it is with three, and now we're starting to, now it's like, if you take your glasses off, maybe you can kind of see, right? And so I'm like, all right, well, now I can't really tell the difference. So here it is, so here I'm keeping more and more, and at some point it feels like, oh, that's actually a reasonable, like, you can imagine this being like the thumbnail version of the thing, right? That's with 10 principal components, and here it is with 12, 14, 16, and certainly we're getting more and more detail. Here's 30 principal components, and starting to feel like okay-ish. Okay, not great, but we're talking about going from 899, so basically 900 down to 30, like 1/30th of the size. Okay, here it is at 50, so about 1/40th of the size, 70, and keeping 90 principal components. That looks pretty good. And once you keep more, here's between 90 and 120, it's hard to really notice any kind of difference. 150, 180, 210, 250. And at this point, going from, like, say, 90 to like 300, 400, or 500. Okay, I think I went up to 500. There doesn't seem to be a whole lot of like additional detail. One thing I am able to kind of see, like on my screen, and maybe you can't really see on the projector, is that it's like you get like slightly improved contrast. Okay, so contrast on your TV screen or your computer screen is basically like how different is the bright from the dark. Okay, and so just naturally in a classroom setting, like contrast on a projected screen is poor. Okay, because I'll ask like, hey, what color is this? And you'd say, oh, that's black. But it's actually the same color as this, which is white, right? And so, like, our eyes, like, I don't know, because of, like, the way our brains process bright and dark, like, in this context, it's dark, but in this context, it's bright. But it's, like, it's the same color, right? In some optical illusion. And so, but on my screen, there's actually, like, I don't know, maybe the dark isn't as dark, but, you know, when you buy a TV, you can buy the $200 TV or the $2,000 TV, and usually, like, the thing that they advertise is the contrast ratio, where it's like when you're watching a movie, like the dark parts will look actually dark and the bright parts will look actually bright, versus the cheaper TV where there's not as much of a contrast ratio. But anyway, if you are looking at it with the principal components, the principal, like keeping all 500 or keeping, like, not doing any dimension reduction, you have better contrast in this image than you do this image. Okay, as far as like fine details of this, maybe you get a little bit like more fine detail in the trees. Like now I can make out some of the individual trees, and over here it's a little bit like fuzzier. Okay, but as far as like real details, not a huge difference. I would say it's a little bit more noticeable as far as like differences in contrast. And that kind of makes sense because contrast in an image is basically the same idea as variation, right? Variation being like the separation from the highs from the lows. And so when you do principal components analysis and you keep more of these principal components, you're able to capture, quote, more variation, which means you are able to distinguish the highs from the lows better than, you know, with fewer principal components. I don't know. I guess that's about it as far as this example goes regarding using principal components as a form of like you can think of it again. You know, we often frame it as dimension reduction, and you know we want to retain the structure of the original data, and you know it makes sense. For me, this felt like, oh, this is kind of a little bit more tangible in that, like, you know, what does it mean to retain the structure of the data, and this is like something that kind of visualizes it. And again, this is not fully recognizable as an image, but retaining the structure of the variation in the original data of like these areas are brighter and these areas are darker, or something like that, where, you know, we're keeping just a few principal components here. And again, it's the idea of finding a lower dimensional shadow, using that shadow to try to go back to the, you know, original dimension. So if you have a two-dimensional shadow and you cut it out of a piece of paper or a piece of cardboard or wood to kind of get a three-dimensional variation, that's fine, right? Like some 3D objects, if I take the shadow of this and I cut it out of cardboard, like I would get the right, like there's no variation in all three of the dimensions. So whether you take this shadow or this shadow, or I don't know, whichever shadow it was, like you can, if you have a thick enough piece of wood, like you'll get it right. But you know, other things, you know, there's not quite. You got variation in the different dimensions, and so, you know, the 2D shadow doesn't produce the 3D object perfectly, but sure. Okay. So anyway, that's that. Something you can kind of play around with. and yeah, like it does reduce the amount of data that has to be kind of carried and imported and sent around, but it is not actually how image compression is run these days, because of the kind of computational expense there. Okay. All right. The next part. So that's that for principal components analysis. Okay, and then this next part has nothing to do with anything that we've really covered in our class, but it was like a fun thing that I went to the R conference, and they were just kind of talking about stuff, and so there is like a lot of desire to harness AI stuff and to be able to kind of use it to write code or help with data analysis and things like that. And so right now, the state of large language models, they say it is the frontier is jagged, is what it's known, and what that means is that it can be surprising as far as like what it can do really well, and it can also be surprising as far as like a task that you thought was simple, but it like does poorly, right? And like I think there's like a common, and this is not like a good measure of any kind of intelligence or anything, but like it's like how many letter R's are there in the word strawberry, and like it performs poorly, and like I think they've gotten it better, but then like I think I saw like another thing where it's like how many strawberries are in the word R, where they intentionally switch these things around, and then so now like if you say how many R's are in the word strawberry, it'll get it right, and they'll say it's 3, whereas like it used to have a struggle with this thing, and now it's like how many strawberries are in the word R, and I'll say there's 3 strawberries in the word R. It's like it does these things that are kind of silly because it's based on these word plays, like the kind of patterns of language it has seen before. I think another one was like there's like this classic riddle that challenges gender biases, where it's like this boy got in an accident with his parent, and he's taken to the hospital, and then the doctor says, I can't operate on him because he's my son, and you're like, oh, how's that possible? And it's like, oh, the doctor's like the mother and not the father, right? But then if you structure a riddle in almost like the exact same way, but then you say like, and the doctor is a man or something, it will still say, if you say, how is this possible? It'll be like, the doctor's his mother or something, right? And it's just because it's identifying these patterns in the language. So, but on the other hand, you ask it a certain question, and it's like writing all of this excellent code that actually works, and it's surprising. So the like compared to a normal human, right? Like we have expectations of like what an 8-year-old child should be able to do. Like the 8-year-old child should be able to count how many R's are in the word strawberry, but not be able to write all of this code. Whereas the AIs like have these weird things, right? Like counting letters and words, it's like at a 3-year-old level, but writing code, it's like at a college expert. So it's just kind of funny. But anyway, all right. So there's a lot of kind of desire to start harnessing all of this power into kind of the tools that we use. And right now, most of our interactions with AI are through like the website. You go to ChatGPT and you type your stuff in, right? Okay. Oh, and look, Microsoft is like, don't use ChatGPT, use Copilot, right? But they're expecting us to interact with ChatGPT through kind of this interface. You know, you have other websites, and Google has Gemini and all of these things. And anyway, we can start to interact with ChatGPT, you know, through R. This requires you to use OpenAI's. No. What do I want? I want to go to. Okay, so you have to. You're gonna have to, in order to do this, you have to create a developer account with, and you can do it with. I think it'll work with a whole bunch of platforms. Okay, and so the package we're gonna use is called Elmer. Okay, where LLM is part of large language models, the name for Elmer, and it's produced by Posit, the people behind RStudio. And but anyway, in order to use it, you do have to create a developer account, and you do have to give them your credit card, and you do have to purchase like at least $5 of compute time. Okay, so I know that's presents a hurdle and some friction, and like you might not want to do it, but it's $5, okay? And you're not going to you just say like this, I'm gonna buy $5, and like when I run out, I run out. And I think it also expires after a year. So, you know, just play around with it. And the $5 will take you pretty far. It'll probably last like a month of you like playing around with it like every single day, okay? And but yeah, it does cost money. So anyway, you'll have to create an account. So you're gonna want to log into the API platform. So you go to OpenAI, go to API platform. Let me see. I'll log out. But basically, so under API platform, you log in, okay? And then I just log in with my Google account, and that's fine. Okay, and then what you'll need to do is under your profile, you'll have to create an API key. Okay, so so I guess you'll have to go to like billing, and you'll have to you know, buy $5. Okay, put in your payment method and stuff, and you can add to your credit balance and whatever. Okay, but you can just start off with $5, and then you will generate an API key. Okay, and so the way this works is you go to API keys, and you'll click create a new secret key. You give it a name. You click create a secret key, and then you'll copy and paste it. Okay, you'll just copy it, and you have to like keep it in your clipboard. I recommend pasting it into like a text file or something, just in case like something happens. And so this is not the actual API key, but like, you know, I just copied and pasted, and I just kind of like made a fake key here. But you're gonna copy and paste it, and then you're gonna want to save this into your R settings, your R environment. Okay, and so in order to do that, there's a library. So you might have to do this. Install.packages, use this. Here, I'll put this, I guess I'll write this thing. Okay, so there's a package called use this. Okay, actually I don't actually want to, I should have clicked cancel, sorry. All right, let's restart R here. Okay, so if you do use this, and then once you install that, you can run use this edit R environment. Okay, and so this pops up here, and then you're going to create a new entry. So probably there's going to be already an entry there, but you're going to create a new entry, OpenAI underscore API underscore key equals, and then you'll copy and paste whatever API key, what's it called? OpenAI gives you, okay? So you'll copy and paste this into there, right? And you'll save that. And then that should get you set as far as running this goes, okay? And so here I'm just running through some examples from the Elmer like documentation, but that's going to be the hardest part, okay? Is just getting, like, you have to create an I don't know, what do you call it? A developer account with OpenAI. You'll have to create an API key, okay? And then you can start interacting with it. And then you have to give them a credit card and buy $5 of credits, okay? And I mean, if you don't want to do OpenAI, like you don't like Sam Altman and whatever, you can go with a different company or something like that. There's Anthropic, there's and they all have kind of similar setups as far as like create an account, give me money, and here's a key, okay? Almost none of them will let you do it for free, okay? Yeah. Question.
It doesn't have any incorporation with like maybe open source ones like Llama.
So it does have incorporation with open source ones like Llama. You can do that. It's just a bigger headache to get the open source. Like if you want to run it locally, yeah, you have to run it, and then the general consensus is that the performance isn't as good. It's like a lot more headache to get it up and running on your own machine, and then your performance isn't going to be good. So yeah, you can save $5 and set it up yourself. And you know, I mean, that could be an experience, a learning experience itself. But if it's like, I just want to start playing around with it, then this is the way. But yeah, there is tools for using what is it, Llama, which is offered by Meta, and then DeepSeek. No, is that the one? Yeah, that's the other, right? So that's open. But yeah, you got it. So anyway, you'll install library Elmer. I guess I'll put that install .packages Elmer. Okay, and then you'll call in library Elmer, and then you can create. Here, actually, let's back up. And you'll create a basic chat interface. So you'll create a chat object, okay? And so there's different ones. We're working with OpenAI, and so we're going to do chat underscore OpenAI, and we'll use GPT-4.1, but you can you can change this up, okay? And then you can change it from chat underscore OpenAI. I think in the reference there's a whole bunch that it will interact with. So there's Claude from Anthropic, other ones that are popular. Yeah, you can do DeepSeek, you can do OpenLlama, yeah, OpenAI. You got, I don't know, these different ones, a bunch that have never heard of, but apparently they're out there. Okay, so yeah, and if you wanna save money, you can even do GPT-4.1 Nano. So that's like I guess that's the cheaper one. GPT-4.1 Nano. All right, so we can do that, and let's see. Here, I'll put echo false. So here, GPT-4.1 Nano doesn't exist, or you don't have access to it. Oh, maybe. What are my choices? Oh, is it GPT-4o Mini? Okay. Yeah, I don't know what the name of this thing is called. Chat with an OpenAI model. Defaults to 4.1. What are my choices? Oh, models. Use models _ OpenAI to see all of the options. Okay, so let's see. Models OpenAI. We have. It's too much. Oh, goodness. There's a lot. Okay, let's try that again. As Tibble. Okay. What do we have? GPT-4o. All right, let's. So we have a whole bunch of. All right. GPT-4o Mini, 4o Nano. All right, sure. We'll try this. I don't know. If you want to try cheaper ones, and then yeah, I think GPT-5 is the latest and probably most expensive. But anyway, so I guess this is how you would name it. Okay, 4.1 Mini. All right. So anyway, you create a chat object, okay, and then you interact with it by just kind of typing in stuff. And is that right? Created R. I don't know, let's see. What is the acceptance rate of UCLA? So here it goes. As approximately 9 to 12% making. All right. Let's see what let's see what it has to say. This is what is the best public university in the world? All right. Let's see what it says. Oh, okay. It just says, all right, here are, all right. Oh, it says Berkeley. Oh, okay. Other highly ranked public universities. All right. And then, so this is all in context, okay? And so you can continue the chat. And so these are all like continuing the conversation. Are you sure it isn't UCLA? All right, okay, so it's doubling down. It says UC Berkeley and UCLA are among top blank. Okay, but most, all right. Is typically ranked slightly higher overall than UCLA. All right. Fine, fair enough. Is undoubtedly one of the best. Okay. All right. So anyway, that is that's that. You can also give it, say, like instructions. So these are system instructions, right? So bterse are system instructions where so here I've created a new chat object, okay, but I gave it the instructions bterse, and so now I can ask the same questions, and now it comes with the system instructions that are much more, and so it's giving me less talk here, right? Acceptance rate is approximately 12 to 14%. All right, let's see. Okay, so it's still saying Berkeley. All right, and then we'll ask, are you sure it's not UCLA? All right, it says, and so this is what it says. Okay, all right. Should I ask about SC? It's not going to be. It'll say it's not public, but right. So anyway, it's so this is your interaction with these things. Okay, and then so you have that, and then. And then, yeah, you can start interacting, and you can kind of format functions to make calls to the the chatbot, and then have the response of the chatbot get kind of formatted back into the thing. So again, this is just an example that I'm taking directly from their documentation, okay? But here it's gonna be built off of just this same bterse thing, all right? And then the clone here will kind of create a new instance, so it's not continuing the conversation, okay? And so here's a function, all right? And it's going to take kind of our existing chat, and then this is a function of like, it's gonna, you can pass in basically arguments from your function into the prompt that you give to the LLM. So here we have a function called capital, all right, and it's going to take our chat object. It's going to create, or basically our chat thing. It's going to clone it and create like a new kind of instance, so it's not continuing a thing. And then this is bterse, and an interpolate is going to basically take this and prompt it to interpolate will take whatever you put arguments you pass into here and put it into this double curly brace place, right? And then pass this to our chat, okay? And then whatever the chatbot returns, it will it's returning basically the response, okay? Okay, but yeah, now it's a little bit like it's a little strange, right? Like the formatting is like, okay, well, I just want this, but it's like giving me a full sentence. In here, it's like, okay, now it's Paris. Okay, but anyway, that is so you can incorporate it into functions here. What are other things? So yeah, programming with Elmer. Let's see. Cloning. Okay, chat objects are R6 objects, and so yeah. So here's that example. Resetting an object. These are conversation. Okay. I don't know. Okay, so that's one example. Let's see. You can also give it like data, but you don't want to ask the LLM to do any actual data analysis. Instead, what you can do is you can ask it to like write code that will help you do the data analysis. So you can say, so what it can be good for is like if you have this really big data file with, let's say, like hundreds of columns, and a lot of times like these public, like these government data sets will have like hundreds of columns, and they all have like terrible names that are like hard to keep track of. But then they also come with like this 100-page data dictionary that what do you call it, defines all of these columns. What you can do is you can send all of that information into basically kind of the system instructions, and you can kind of load it up and say, all right, take, read through this data dictionary to understand the column names. And then when you write prompts, you can say, can you tell me which columns I should select for if I want to get demographic information on race and age or something like that. And then it will scan through basically all of the documentation and say, these are the relevant columns, and it will write some R code or whatever code you want to execute that. And so that would be a better use case versus asking it directly, try to analyze this data set, because if you do that, it doesn't perform well right now. So, but as far as like writing code to accomplish a task like that, it's good, and it's very good at kind of just like reading like big boring documents and understanding kind of context and meaning from that. I don't know. Any kind of questions on this? This is just kind of like a fun thing to, I think, I don't know. Maybe the AI bubble is going to burst and whatnot. And I think there's a whole bunch of like little startups like trying to run on the AI hype train. And I think they're probably going to die. But I do think like using AI LLMs, that is like a big thing, and it's going to get more and more, I don't know, important that we understand how to use it. Yeah, question.
Can you talk about why, or like the advantages of having it kind of integrated into R versus like just using like an LLM from like a website?
Yeah, I mean, so the reason for wanting to do it this way versus, I mean, so these are like dumb use cases where I'm not getting any like better interaction than like just talking on the ChatGPT website. Yeah. No, but what it can do is you can kind of go back and forth between, like, let's say you have data in here that needs I don't know, interpretation or some processing. There's a, I wonder if I can find this example here. I'm sorry. Okay. Oh yeah. Here's a good example. Okay. So let's say you had this thing where people write their responses and they're talking about their ages, okay? And so here, and you can imagine this, right? It says, I go by, like we say, hey, say your name and introduce yourself. Say your name and your age, right? And then so they say, you know, all kinds of stuff, right? I go by Alex, 42 years and counting, okay? Pleased to meet you. I'm Jamal, age 27. They call me Li Wei, 19 years young. Fatima here, just celebrated my 35th birthday last week. The name's Robert, 51 years old. All right, Kwame here, just hit the big 5-0, right? And so how do you go through this and extract out the name and the age? This would be really painful to do. Like you can't use regular expressions. Like it's just too complicated, just because like sometimes the name has a space in it. And like you can say like, all right, search for numbers, but this person spelled out 19 and this person annoyingly put 50 for, you know, to say 50, right? So this is a place where you can say, all right, here is this information, okay? And we want to ask a question, and we want the responses to come back structured, okay? And so we are going to say, all right, create type object, okay, where we're going to get the name. That's going to be a string. The age will be a number, okay. We're going to interact with chat OpenAI, and then we're going to ask to try to extract out this stuff here. And it does it, okay. So it says, yeah, using model GPT-4.1, and it manages to kind of parse through all of this stuff and extract out the name and the age. So this is kind of a thing. Yeah, I suppose you could take this, put it into ChatGPT, export it, and get it back, right? But you might have this kind of weird, soft, unstructured data or something, right? Like maybe you have movie reviews or something, right? You have all of this kind of text stuff, which is notoriously kind of difficult to parse through. But if there's like certain things that you're looking for in these, I don't know, sentence, document, paragraph type things, and you're saying, I'm looking for the name or the age or whatever, you can structure it and pass it and use basically the LLM's ability to like understand English and get these things out, which is great. You probably should double check certain things, but yeah, it at least for this fictional example, kind of handcrafted to take, it seems to work well. So and then now this is in a data frame that we like to work with, right? We like to work with tables of stuff. So yeah, lots of neat little kind of use cases. Yeah, so yeah, structured data basics, yeah, is on this.
I've heard that like with a lot of the movement in LLM is towards like a sort of like a agentic approach, like equipping it with a lot of tools and stuff to like give it functions to call. Is that something that you feel like R is suited for?
Yes. Okay. I wonder. Okay, I need to find more examples. There is. Let's see. Yeah. Okay. So there is the ability to call tools, or yeah, in this agent form. Okay. So for example, right? Like if you ask like, what's the weather right now at Fenway Park? Okay. If I just say, hey, chat, like, or like if I just say, hey, what's like, this is not going to I don't think it can do it, right? What is the what's the weather right now in Westwood, Los Angeles, CA? All right. Okay, so it's gonna say, yeah, sorry, I can't provide real-time weather updates, right? Okay, but what you can do is okay, so it says, how long ago did Neil Armstrong touch down on the moon? It says Neil Armstrong touched down on the moon on July 1969, and then it says as of October 2023, that occurred 54 years ago, but that doesn't work today because it's not October 2023, right? So what we can do is we can give it a tool that basically, so here's the example where it's not going to work well. Oh, look at that. It has figured out, no. Okay, today's date is June 21st, 2024, right? So it's trying to do something, okay? What in the world? Okay, yeah, so something, this is weird, right? It's like July 20th to this. Okay, 54 years and 11 months. So, okay, approximately 54 years and 11 months ago, okay? Obviously, that's not gonna, that's not correct. But we can give it a tool that's like, all right, let's figure out what the current time is, okay? So we can give it this time that just says, hey, get current time, and what is the current time here? Okay, that's UTC. All right, so let's, what is our time zone here? PDT? Are we daylight time? No. Pacific Standard Time? I don't know what our time zone is. What our letter time is. Pacific. It hates me. Okay. All right, whatever. Let me just ask. Chat, $chat. What is the POSIX abbreviation for Pacific time zone? PST UTC -8. Okay. All right, so let's try. Okay, stop talking. Oh, PST 8 PDT is the, okay, that's the one we want. All right. Okay, so we'll try it. Get current time. Oh, okay, yes, that's the one. All right, thank you. Okay, so we can do this 1208. Yeah. All right, so that's what we have. All right, so now we have this tool, and then now we have a way to call the time, and we're going to basically turn this into a tool that so I'm going to change this here. Make it a tool. Turn this function into a tool that our LLM can use. Okay, so we're going to turn a tool from get current time into the get current time tool, and it's going to basically time zone to display the current time in, defaults to UTC. I guess this is what we have. All right, maybe I can put that in here. So this creates a tool here. Okay. So this is. It says this is a fair amount of code even for such a simple thing. Okay, but it's just a special type of tool, and so we can still call it. And yeah, it's still working. Okay, so we register the tool with our chat. Okay, for get current time, and then now we can ask the question: how long ago did Neil Armstrong touch down on the moon? And then, and now that it wants to figure out how to get the current time, okay, returns the current time and whatnot. It understands this as a tool. It says it's doing a tool call, and it says this was, July 20th. Today's September 9th, and now it can return this. So there is, the power to kind of incorporate tools into your function calls or whatever, or your chat calls is possible. And yeah, again, these are just kind of like examples to get started. And yeah, it said you can see kind of like the what exactly is going on, and it says so far, right? So these are all of the things that I asked. Okay. Okay, so there was that, and this. Okay, so now we said this, and this is how long ago did this do that, and then so now it says, okay, we want to get this time zone. The tool result is this, and so now that it has this information, this is how it returns the response here. Okay. Yeah, so there's more examples. What's else in here? I don't know. Oh, okay, so here's another tool as far as getting weather. Okay, so get weather is a tool where we're gonna kind of look at I guess different kind of cities and what is this? Raining. Okay, so this is slightly more complicated. That uses get weather to return data frame. Okay, all right. So yeah, I guess you might have something where it basically takes JSON information and incorporates it. So yeah, it's probably going to require a lot of like fiddling around and manipulating. But yeah, I mean, all of these things are going to be like you have your imagination and you have certain tools available to you, and can you kind of like creatively use them to get what you want. But anyway, it's just kind of like a fun thing right now, but certainly, yeah, you might be able to do something really cool. I think so. Just some encouragement there as far as getting to interact, and basically these packages like Elmer, and then if you want to do Python, the one is called Chatlaz. And it allows you to kind of do something similar. Okay, similar kind of thing, but for Python, where you can interact with all of these other all of these LLMs and stuff. Okay. All right. Yeah, that's about it. Yeah, if you guys come up with something cool, let me know. I want to see. All right. All right. Thanks, everybody. Are you still able to leave reviews, or is that like already closed? I don't know how it works. But anyway, thanks for a great quarter. Good luck as you guys study, and we'll see you on Thursday for the final exam.